Okay, let's jump right into this explainer because today we are tackling one of the absolute most profound mysteries of existence. You look around, right, and you see life literally everywhere. It's vibrant, it's highly organized, and it's incredibly complex. But when we zoom out and look at the fundamental, foundational rules governing the universe, there's this startling contradiction. So today, we're going to explore biological systems through entropy, and I promise you, we are going to uncover a perspective that might just completely change how you view every single living thing on Earth. And this immediately brings us to a massive, towering question. Why does life exist in a dying universe? Because, the universe is governed by this ultimate rule dictating decay and disorder. Given enough time, everything is supposed to break down and spread out. So how on earth do complex, highly organized living things even exist? How do they not just survive, but actually thrive, evolve, and get increasingly intricate in a cosmos that essentially demands their destruction? Section 1. The Paradox of Life. So let's unpack this incredible tension between the cold, hard laws of physics and the vibrant reality of biology. To really grasp this, we have to talk about entropy. You're probably familiar with the second law of thermodynamics, which dictates that matter and energy constantly disperse toward a state of maximum disorder and uniformity over time. Basically, in nature, things naturally break down. It's exactly why sandcastles eventually crumble in the wind, and it's why your hot cup of coffee is inevitably going to cool down to match the room's temperature. It is this inescapable, invisible force driving literally everything toward equilibrium. Now, way back in his 1944 book, What is Life?, the Nobel laureate physicist Erwin Schrödinger posed this exact paradox. He realized that life actively fights this natural decay by feeding on what he initially called negative entropy. Decades later, scientists like biochemist Albert Lininger refined the concept. They explained that living things actually maintain their internal order by taking in concentrated, free energy from their environment, like nutrients or sunlight, and then returning an equal amount of energy back out, but as messy, chaotic heat. Moving on to Section 2, Open Systems and Entropy. Let's look at how biology exploits a massive, built-in loophole in physics. This loophole brilliantly shows us why life actually doesn't violate physics at all. See, the second law of thermodynamics strictly applies to closed systems. Imagine an isolated box where no energy comes in or goes out, but biological organisms, we are open systems. We constantly interact with our environment. This means a living thing can maintain or even increase its own local internal order, just as long as it takes in external energy and greatly increases the entropy of its surroundings by dumping heat outside. By looking at the Gibbs free energy equation, which is essentially a cornerstone of chemical thermodynamics, we can see exactly how this mathematical balancing act works. Biological processes create immense internal organization by basically acting as a conduit. Take a plant, for example. It takes in highly concentrated, low-entropy energy like sunlight, uses it to build complex structures like sugars, and then ejects chaotic, low-quality, high-entropy infrared sheet. The math perfectly balances out. The universe's total disorder goes up, even as the organism stays highly organized. All right, Section 3, Dissipation-Driven Adaptation. This is where the story pivots to why life might have originated in the first place. So we've established that life is an open system that dissipates heat. Well, MIT biophysicist Jeremy England proposed a breathtaking paradigm shift based on this. He moved the conversation from how life survives entropy to why life might have naturally originated from it. His theory of dissipation-driven adaptation suggests life isn't just some random accident or a lucky lightning strike in a primordial soup. Instead, under the right conditions, matter will inexorably acquire lifelike physical attributes simply because it's the most efficient way to maximize energy dissipation. Basically, life might just be the universe's absolute best engine for increasing entropy. The truly crucial takeaway here is that you don't necessarily need magic to spark life. Think about it as a sequence. Step 1, you have a random clump of atoms. Step 2, you introduce a constant external energy source, like the sun. Step 3, you have a surrounding heat bath, like the ocean or the atmosphere. If you shine that light on those atoms long enough, Step 4 dictates they will spontaneously restructure themselves into a system, like a plant or a bacteria that is incredibly, uniquely good at absorbing that energy and releasing it as heat. Which leads us nicely into Section 4, Life as an Engine. Let's really lean into the thermodynamics here. When we look at living things through this very specific lens of physics, seeing them as machines designed to process energy, a lot of really familiar, complex biological traits start looking completely different. They're essentially just a grab bag of specialized physical behaviors designed to route and dissipate energy. I mean, why do organisms self-replicate? Because making copies of yourself is a fantastic way to dissipate even more energy. Why harvest fuel or predict the environment? To secure a constant energy stream. And homeostasis, like healing a wound, is just using that fuel to constantly undo the microscopic thermal degradation that's always trying to tear the organism apart. And look, this isn't just abstract guesswork. Thanks to cutting-edge non-equilibrium statistical mechanics, specifically the fluctuation theorems developed by physicists like Chris Dzerzhinsky and Gavin Crookes, we actually understand this mathematically now. These theorems prove that when systems are driven far out of equilibrium by an external energy source, they naturally evolve along trajectories that dump more and more heat into their surroundings. They literally adopt configurations that are highly irreversible simply because of how much energy they pump out. What is truly mind-blowing here is the connection this makes between the living and the non-living. Just take a look at this table. Living things like DNA and plants share the exact same physical mechanisms for energy dissipation as inanimate, completely non-living phenomena. A plant using photosynthesis or DNA using polymerase repair are thermodynamically doing the exact same thing as a turbulent fluid vortex, a snowflake forming, or a sand dune shifting in the wind. They are all just structured patterns that emerge in driven systems to dissipate energy. Let's actually zoom in on a plant to see this in action. A plant uses solar energy not just to grow leaves and get taller, but to fuel a massive, invisible internal engine. It uses that energy to power these things called molecular chaperones, which are complex structures constantly proofreading and repairing the plant's own misfolded proteins. It is continuously burning chemical fuel to correct microscopic decay. It is constantly fighting back against the chaotic, destructive forces of thermal fluctuations every single second, just to stay in one piece. And finally, Section 5, a thermodynamic meaning. Let's talk about finding real value in these cold physical laws. You might be wondering, how do we reconcile these cold mathematical mechanics with the awe-inspiring, deeply felt experience of actually being alive? I mean, does reducing life to a thermodynamic heat engine make it all sort of meaningless? Well, let's bring back Jeremy England for a second. He points out that the fuel-consuming, heat-dissipating activities lie at the core of what living things are doing all the time. But England, who is actually an ordained Orthodox rabbi, strongly argues that stripping life down to a thermodynamic equation absolutely does not rob it of its beauty or its transcendent meaning. Science gives us the mechanism, it doesn't erase the value of the experience. Actually, we can find a profound intellectual resonance between non-equilibrium statistical mechanics and human existence. By understanding that our existence is perfectly harmonized with the universe's ultimate laws, we connect even deeper to the cosmos. We aren't some weird temporary mistake fighting against the rules of the universe. We are a fundamental expression of physics itself. We're localized pockets of brilliant order, operating exactly as the laws of nature allow. So the next time you take a deep breath or feel the warmth of the sun on your skin, I want you to look at the world around you. Look at the trees, the animals, and really ask yourself this final provocative thought. Are you just the universe's most beautiful way of cooling down? It's a remarkable way to view our place in the cosmos. Thank you so much for joining me for this explainer. Keep asking those big questions, and I'll catch you next time.